Okay, let's dive right into this. Welcome to today's explainer. I am beyond excited for this one, honestly, because we are looking at an absolute efficiency monster today. We're going to tear down the architecture of a groundbreaking, completely free 30 billion parameter AI model from NVIDIA. Now look, there are a ton of models out there right now, but this one, it's special. It effortlessly juggles images, video, and audio all at the exact same time, and it does it at speeds that, frankly, make traditional models look like they're walking through molasses. If you care about high-speed, cost-effective multimodal processing, you are absolutely in the right place. Let's get into it. I mean, just look at this jaw-dropping stat right off the bat. 10 hours. This new model processes almost 10 hours of video in just a single hour of compute time. That literally means it operates at nearly 10 times real time. If you've ever sat there agonizingly watching a progress bar slowly crawl across your screen while processing video data, you know exactly how insane that is. It completely shatters our expectations of what a localized, free model can actually do when it comes to pure throughput. To put that into perspective, let's compare it against the competition, like the highly respected QN3 Omni. This speed is just a massive leap. The new 30 billion parameter model is almost 3 times faster for video processing. And if you're processing documents, forget about it. It's up to 7 times faster. We are talking about a monumental leap forward in both speed and cost efficiency.
So you're probably wondering, how exactly are they pulling this off? Well, here's our roadmap for the explainer. We'll cover linear scaling, how they're rethinking audio and image, their smarter video compression, and finally, the hardware needs and limits.
Starting off with Section 1, Linear Scaling Explained, and how they solved the math bottleneck. But before we get into the scaling, let's quickly make sure we're on the same page about context length. Simply put, this is the total amount of information, whether that's huge stacks of documents or thousands of video frames, that an AI can essentially hold in its working memory and process at any one time. The larger the context length, the more the AI actually understands the big picture of what you're feeding it. Building on that, let's look at technical innovation number 1. Older models relied on traditional quadratic scaling. So as context length grew, say you fed it a feature-length film, the computational cost exploded quadratically. It gets ridiculously expensive very fast. But this new model utilizes linear scaling. The takeaway here is absolutely crucial. You can throw everything you have at it. The longer the video, the more documents you feed it, it doesn't matter. It remains highly efficient. If you're running mass-scale document analysis or looking at long-form video, this linear scaling is a total game changer. Moving right along to Section 2, Rethinking Audio and Image, bypassing the legacy Goliaths. Let's talk audio first, which brings us to innovation number 2. Traditionally, systems rely on a massive, separate speech recognition model to handle sound, like the very popular Whisper model. But Whisper is huge, it's pricey to run, and honestly, the biggest flaw, it often strips away all the emotion and tone from the input, leaving you with just cold, flat text. This new AI bypasses that entirely. It converts raw audio waves directly into tokens. It's drastically cheaper because you aren't running a whole separate model on top of everything else. And best of all, it retains the original emotional context and tone of the speaker. Okay, what about images? Normally, you'd expect to see a giant, standalone clip model whose whole job is to predict what text matches an image. It's an industry standard, but again, it is computationally super heavy. Instead, NVIDIA threw that out. For innovation number 3, they replaced it with a highly distilled 3-in-1 encoder. And what this distilled encoder actually does is fascinating. It's kind of like a Swiss Army knife. The engineers effectively smashed 3 highly specialized functions into one tiny, incredibly efficient neural network. It handles image-to-text matching, it extracts really fine details, and it performs complex object segmentation. All 3 of those tasks neatly packaged into one small encoder. It really is a masterpiece of efficiency. All right, Section 3, Smarter Video Compression. Let's stop wasting compute, shall we? Just notice the elegant simplicity of their approach here. Previous generation techniques would wastefully smash your media into brand new standardized aspect ratios before even processing them. That is a massive waste of compute. This new efficiency model simply retains the original aspect ratio of your images and video right from the starting line. No extra processing step required. It's so simple, but so smart. But here is where it gets really brilliant with innovation number 4, 3D convolutions. See, traditional AI models often process video frame by frame by frame. It's a monumental amount of computation. 3D convolutions, on the other hand, act as an optimization that looks at packages or blocks of video frames simultaneously. Because it's analyzing chunks of time all at once, it can compress the video data far faster and drastically cheaper than the old frame-by-frame computational grind. And that perfectly sets up their next trick. Innovation number 5, efficient video sampling. Think about it like this. In step 1, you input a chunk of video, let's say 300 frames. But not all 300 frames are completely unique, right? So in step 2, the AI identifies duplicate backgrounds, like maybe a static wall behind a person who's talking. Then, in step 3, it just throws away that duplicate information. It doesn't waste time analyzing the exact same background pixels 300 times. Tossing out that redundant frame data makes the entire system drastically cheaper to run. Okay, section 4, hardware needs and limits. Let's talk about the reality of actually running this beast. 25 gigabytes. That is the strict video memory, or VRAM, requirement, and it makes it very clear that this model is built for serious hardware. With a 25 gigabyte requirement, there is just no way you're going to run this locally on your smartphone or a standard entry-level laptop. So what are your actual options to meet that 25 gig threshold? Your hardware recommendations generally fall into 2 paths. For local processing, you are going to need a seriously beefy desktop GPU. However, if you don't have a massive local GPU sitting on your desk, that's completely fine. Services like Lambda Cloud instances are highly recommended. They're basically perfect for spinning up the necessary compute power entirely in the cloud so you can run your experiments or chatbots without dropping thousands on a graphics card.
Now, what about the red tape? When it comes to licensing and limitations, I'd personally score the custom license a 7 out of 10. For context, an incredibly permissive, true open-source Apache 2.0 license would be a perfect 10 out of 10. So yeah, while it's not a fully permissive 10, a 7 out of 10 is actually a lot better than you might expect for a cutting-edge model of this caliber.
Neutrally speaking, here is the actual fine print that developers need to know. The really great news is that derivative works and commercial use are fully allowed. You can literally build businesses on top of this. However, it does require a bit of attribution, and it is noticeably stricter on patent grants compared to an Apache 2.0 license. So just make sure you're aware of those rules before you start deploying anything into production. Also, just to maintain total objectivity here, we definitely have to talk about what this model is bad at, because it's not perfect. This is not recommended for pure text reasoning or pure coding tasks. If you just need a really smart model to write Python code or reason through complex textual logic, you're going to want to look elsewhere. It just isn't the smartest model for those highly specific tasks. Its true superpower is processing multimodal inputs, like your audio, your video, and your images, super fast and super cheap. Which brings us to a really fascinating conclusion. The immense value of now being able to own specialized, high-speed, multimodal AI locally, it just cannot be overstated. We are getting more models, more value, and more specialization totally for free. But I want to leave you with this thought-provoking question. As models like this one become incredibly specialized, highly efficient, and perfectly tuned to run on local hardware or affordable cloud instances, what does the future actually hold for those giant, monolithic, jack-of-all-trades, cloud-based AIs? Think about that, and I'll catch you in the next explainer.